Do you remember interesting chess battles between Kasparov and Deep Blue? I'm sure you do. The first movements are simple, yet the most important. They determine how strong you are going to be at the end of the battle. The same occurs when designing IoT devices embedding antennas. If you want seamless connectivity, data into the cloud, range, battery life, you should consider the antenna system from the very beginning to optimize the radio performance of your device. Hi, my name is Jaume Anguera. I am co-founder and CTO at Fractus Antennas. I am glad to be here from the nice city of Barcelona. And in today's presentation, we are going to learn how to expand the connectivity of your LoRa device embedding virtual antenna. The topics we are going to learn is why virtual antenna changed the deal, what are the virtual products we can use either in LoRa devices or other kind of IoT devices, what is the virtual antenna architecture, how from an engineering perspective we can embed virtual antenna in a very simple 1, 2, 3 steps, some electronic design automation tools that you can use for your own designs. And then we are going to see a very nice example of the sensor development platform, which is the generic node using virtual antenna. As well as the end, we are going to compare virtual antenna technology with other antenna technologies. And finally, some takeaway. So let's go. Why virtual antenna is so disruptive? Let's go back in time, 40 years ago, back in 1983, with the apparition of first external monopole antennas, large antennas, easy to break, easy to steal. And then back in 1996, 1999, suddenly they appeared the first internal antennas customized with complex geometries and single band for the GSM application. As the time went on, when we have, again, this kind of customized complex antennas, the volume was reducing and they were multiband. But the big breakthrough is with the apparition of the virtual antenna technology back in 2013, where you can see that these antennas are internal components and 10 times smaller than other antenna technologies. Also, they are multiband, they are off the shelf, so it's very attractive for embedding the antenna on a PCB. And very important feature is that besides being small and multiband, they support multiple radios in a single component, as we are going to see today. So why is so disruptive and how we can help the IoT market to grow faster? Virtual antenna is based on these tiny components called antenna boosters, you can see in red, that can be easily embedded on a PCB to operate band and for any device. Let me explain. In this picture on the left, you have several devices, several PCBs, representative of IoT devices, from a big one to a small one. So no matter the form factor of the device, we don't need to use a different antenna for every device. With the same antenna booster, we can have operation, and the only thing we need to customize is a matching network. But by the way, this is easier, faster than designing a customized antenna or designing antenna from the scratch. Another attractive attribute of virtual antenna is that the antenna booster can operate for any band. It's not the antenna that gives the frequency band of operation, but you, as a designer, can freely choose the frequency bands where you want to operate. For example, imagine you have this device and you want operation at LoRa frequencies, LoRa bands, then you design a matching network for your device, which is easy and fast. But you want to update this device for a new project, and you want to do, for instance, cellular IoT frequencies, a multiband. Do we need to change the antenna geometry? Do we need to customize the antenna? The answer is no. We can use the same antenna booster, and the only thing we need to change is the matching network. And as we're going to explain today, this is very simple, easy, and systematic to do. So as you can see, virtual antenna, it's small, it's multiband at the frequencies you want, from single band to multiband. It's an off-the-shelf component, and it's pick and place. So it's suitable because it can be mounted on a PCB as any other chip. It's an amplifier, a filter, a system on chip. Let's see the product portfolio we have in virtual antenna. In here on the top, you have the products for different form factors. Depending on the application, there are some antenna boosters that are more suitable than others. For example, in this case, the cube, by the way, it's a tiny component, only by 5 millimeter, very, very small in size. These first three components, the cube, the RAN, and bar, are suitable either for single band LoRa application and for multi-band application. Also, we have a very attractive antenna boosters, the Trio MX10 and the Duo MX10, that they are multi-radio antennas. For instance, the Trio can operate at the same time at 3 radios, as we are going to see now. The Duo, for instance, pretty small, it's 7 by 3 by 2, high only, without clearance on the PCB, can operate simultaneously at GNS satellite frequencies, GPS, Beidou, GLONASS, plus Bluetooth in a single component. And finally, this little child here, it's called the One. It's 7 millimeter by 3 millimeter by only 1 millimeter high. By the way, this guy is the one that is in the generic node, as we are going to see, and I think you saw in the nice presentation of Orkan of the Things Network, and also our colleagues from ST Microelectronics. Also, we invite you to visit our webpage. It's plenty of user manuals, as well as many application notes, easy to read. And for instance, you can have a look what is the impact of the PCB size on the performance in terms of efficiency, bandwidth, so you can have a flavor on how to determine the correct PCB size for your LoRa device. Let's have a particular deep dive in this Trio MX10. To scale your business in IoT, we saw in this conference that you need several attributes. One is certification, another is security, and one very important is what is called a multi-radio access network. And in this case, you know that Semtech transceiver, the Semtech LR 1110, provides 3 radios on a single system on chip. In particular, the Semtech transceiver has a LoRa input-output, the GNS for satellites, GPS, GLONASS, Beidou, also another for Wi-Fi. So 3 radios in a single package. Do we have an antenna booster that can handle the 3 radios at the same time? Yes, this is called the Trio. The Trio MX10, the Trio antenna can handle simultaneously the 3 radios. So let's illustrate this with this picture. This is a pain for our customers in the past. If they need to use 3 radios, a radio for LoRa, a radio for GPS, and a radio for Wi-Fi, they need to use 3 transceivers and 3 antennas. So as many antennas as communication system. This is a nightmare, and it's difficult to scale with this kind of approach. So Semtech, very intelligent, did a transceiver that combines all 3 radios in a single chip. And also we did that. So what we did is, okay, let's match this nice transceiver with 3 radios with our Trio MX10 that can handle the 3 radios. So with one port, you can handle LoRa. With the other, you can handle GPS. You can receive signal from GPS, Beidou, or any kind of satellite system. And also with Wi-Fi, with a single component. So you can imagine in this picture, it's clearly illustrated. You don't need 3 antennas. You only need 1 antenna. You only need a small area to integrate. In this case, you need area in a small IoT device that they are very small. So it's difficult to integrate several antennas. This is faster to design, and it's a compact solution. So easy to scale with this kind of approach of the Trio MX10. We invite you to have a look, to keep an eye on the application note that Semtech, together with Fractus antennas, is going to publish an application note that explains in details the behavior of the transceiver, the Semtech LR 1110, in combination with the Trio MX10 for LoRa, GPS, and Wi-Fi for several PCB sizes, even with the presence of concrete, wood, plastic. It's a very nice application. So have a look, and if you have any question, you can always reach us. Now that we know a little bit about the products, let's move about the architecture of a virtual antenna system. We have the antenna booster that you saw before. This is a very important component of the architecture, but we have two more components of this architecture. The matching network. The matching network is the combination of components, inductors and capacitor that allows us to choose the frequency band of operation. And the third one is the ground plane of your device. The size of your device matters. So let's have a look, now that we know the antenna booster, at the matching network and at the ground plane, how this both matters when designing your LoRa Edge device. As we said before, antenna booster, you can see here how small they are. The frequency is not given by the antenna booster. It's something that you as a designer can fully choose. And how you can do that? By the addition of a very simple matching network. In this case, if you use a simple matching network, which is a combination of very tiny passive components, capacitors, and inductors, you can go from either a single band response at LoRa frequencies, perhaps you want to go beyond and include cellular IoT bands in a multi-band fashion, and also expand your bandwidth and include more bands. Everything can be easily done with a combination of antenna booster, of course, and with the addition of a matching network. The third component in this architecture, antenna booster, matching network, the device is very important. Why is so important, the device? Because the size of the device impacts the efficiency. So at the end, it's data to the cloud, range, battery life. This impacts a lot. So to give a flavor, we have in this plot, we plot the efficiency from 0 to 100%, which is the best case, versus PCB area from a very small one, 10 centimeters square, to a large one. As you can see, as you go from a small PCB to a small device to a larger device, how efficiency can impact. So as designers, we should have this graph into account from the very beginning and not only put into the decision the roadmap of marketing, but also consider the efficiency, this plot, to take action, because the device size matters a lot, and it's difficult to make changes when you are in development or if you are at the end of the project. If you need to take a decision, you should do the decision, remember, at the very beginning, as the chess game. So consider this as a rule of thumb at the very beginning of your project. Let's see some examples of matching network. In this case, for LoRa, we have here a bare PCB. We have an antenna booster, and here we can put the lamp components, the matching network, and by the addition of a very simple matching network, we can operate at LoRa, European frequencies, US frequencies, with a very nice efficiency. You can see the efficiency in blue of about 90%. And imagine you want now to have another device for cellular IoT frequencies. You can use the same antenna booster. As you can see here, we have the same device, the same platform, the same antenna booster, and the only thing we need to change is the design of the matching network. So by doing this, which is simple and fast, you go from a single band to a multi-band, in this case from 900, 1800, and 2 gigas. And even more challenge, you can expand the bandwidth, reaching most of the LT frequencies, LT bands, by again changing the matching network. You see, everything is the same. The PCB was the same, the antenna booster is the same, and we only customize the matching network. As you can see, antenna booster in combination with a matching network and the ground plane are the essential parts of a virtual antenna architecture. Now that you know what are the parts of the virtual antenna, let's see how we can embed in very simple steps virtual antenna in your LoRa device. First step is to select the best antenna boosters. Depending on your application, on your device size, there are some boosters that are more convenient than others. And the position of the antenna booster on the PCB matters. Usually, as a rule of thumb, the corners of the device are the best positions. Second step is design of the matching network. The matching network is something that should be placed between the antenna booster and the transceiver in order to maximize the signal going to space and also to maximize the signal coming from the air. And finally, you can test your device, either with a vector network analyzer, you can tune the matching network needed with your real device, and finally, also you can test the radiation patterns, efficiency in an anechoic chamber. We invite you to have a look at these 3 nice videos that are available in our YouTube channel, 1-minute video that explain with more details these very simple steps. Also, if you want to get more information, we have this general paper that you can have a look at it. Let's illustrate the position of the antenna booster. And here what we have is very nice real examples, in this case from Nordic Semiconductor. This is a Thingy 91. This is the Trio X10 antenna booster in red, and always we try to fit at the corner of the device. In this case, we have this antenna booster, the LoRa X10 for IoT cellular application. This is the yellow, mango yellow by Sierra Wireless. As you can see here, the feeding line goes to the corner of the PCB. And with more detail, again, the Trio, the feeding line, and in here, between the module, which has been removed in this picture, between the module and the antenna booster, we have a matching network. In this case, it's again for a multi-band IoT applications. Another example with the LoRa X10, we have fully populated transceivers, SIM cards, and whatever. You have the antenna booster, again, fed at the corner, matching components, a 50 ohm transmission line that reaches your transceiver. So as a rule of thumb, placing the antenna booster at the corner is the best option to maximize bandwidth and efficiency of your LoRa device. Now, let's see about the matching network. As we said, antenna booster are non-resonant elements, they are frequency neutral, is the designer, you, that you can freely choose at the frequency of operation. Let's illustrate this. This is a PCB, this is antenna booster, and without any matching network, if we go to this picture, you can see that the S11 is completely mismatched. It's far away from the center of the 50 ohm, and 1 and 2 represents LoRa frequencies. But with the addition of a matching network, we can easily move this impedance to the center of the Smith chart. As a result, the S11 can go from a very poor match, you can see here, without matching network, it's a very poor matching, about -1 dB in terms of S11. And with the addition of a matching network, we can improve to a very good values below -10, -12 dB. So with this, you can ensure that your transceiver is going to send data into the cloud, you will have battery life, you will have range, and you will have also the signal from the air. So the performance of the device is optimized. Now that we have the knowledge about the virtual antenna architecture, let's move on the topic of what electronic design automation tools we have for you to help to embed virtual antenna in your device, from conception to mass production. And we have these four EDA tools. The first one, it's the libraries. I'm sure that you are familiar with circuit simulators such as Cadence Microwave Office, perhaps Opteni, Keysight ADS, where is plenty of libraries for inductors, for capacitors, filters, amplifiers, and so on. But never for an antenna, never for an antenna. Now is the first time ever that a library of antennas is included in a software by Cadence, by this example, thanks to the unique attributes of virtual antenna. And this library is a set of S parameters representing a wide bunch of platforms. So we have a variety of platforms representative of many IoT devices, where you can also combine with any of antenna boosters. So once you decide which PCB and which antenna booster, you have a file, a S11 file that you can import in your software, and you define the frequency bands you want to operate, you define the target of your S11, and by using network synthesis tool, you obtain the matching network. So even you don't need to design the matching network. The software is going to design the matching network, the topology, even with commercial components. Let's illustrate this by steps. So imagine the library has more than 40 PCB sizes, and let's illustrate the generic node. So perhaps you are designing the generic node, you have an idea in your brain, and you want to test your idea if with the PCB size, you are going to have enough bandwidth. Remember, the ground plane, the size of your device matters. So it's very important at the very beginning to have a tool to test if you can get enough bandwidth. So with this, you can do it without having any mock-up, without doing any prototype. So we find out in this library that there is PCB file that it looks very similar to our generic node platform. Okay, and for our generic node, we want to have LoRa, and we decide to go with this antenna booster. This is the one MX10. It's 7 millimeter only by 3 millimeter by only 1 millimeter. Okay, so we say in this library, we want to model the generic node we have in mind, which is 61 by 35. In the library, it's 60 by 35. It's very similar with an approximate position of the antenna booster. And once we select this, what we obtain in return in this library is an S file containing all data from a very low frequency, 0.6 giga, up to 10.6 giga. So you can play with LoRa, or perhaps you can play with other protocols. If you are interested in these libraries, you can download for free from our web page for any kind of software. These files are compatible with Cadence AWR, Opteni, Keysight ADS, and any kind of circuit simulator you are using. Let's summarize the steps, and then we're going to illustrate step by step the LoRa design, the generic node design. We select the PCB, we select the antenna booster, then we define the frequency bands we want to operate, we specify the target, and that's all, because step 5 is telling the software to synthesize a matching network. And using artificial intelligence, some kind of genetic algorithms, in return, it gives the topology of the matching network, the values, and even if you want to use a particular vendor, Murata, Coilcraft, whatever, you can also decide which vendor, and in return, it gives you the components that you can use for future testing. Let's see the particular example for the generic node. We have the generic node. We have selected the PCB in our library. It's 60 by 30. It's very similar to the generic node platform. We choose the antenna booster D1 because it's very small. By the way, it's lambda over 50. This is pretty small. Then we define the frequency bands. In this case, we are going to do an example for LoRa European frequencies, 863 to 870, and we define a target of S11, for instance, -7 dB. And that's all, because we tell the network synthesis to do the matching network for us. Let's illustrate in this nice video. This is how the S11 file looks like. It's a black box containing the S11, the impedance data for the one on the PCB 60 by 30. And let's run this video. Let's have a look. And this is the file without any matching network. This is the first time ever that you have antenna library. You can see here, embed in a circuit simulator. We have components. In this case, we have the Fractus antennas virtual library embed in Cadence AWR. We see the S11 is very poor because we don't have any matching network. And we're going to do it, we are going to synthesize a matching network. We go to the network synthesis tool. We specify a wide frequency range. Also, we can choose components. How many components do we want? We say maximum 4. If there is a solution with 3 or 2, the software will tell us. Also, we can say, well, inductor and capacitor up to this value, no more than 50 nanos. So it's quite practical. And the goals. And in this case, we define the goal. The goal is I want an S11 below minus 7 dBs, in this case, in the frequency range of LoRa in the European bands. So we say here, we specify the frequency range of LoRa, and the goal, which is the S11, we want the S11 to be below, if possible, below minus 7 dBs. If there is a solution, the software will find for us. In a very fast way. This is very systematic, as you can see. Here we have a clock, by the way, it's 3 minutes to see how fast we can do it. We optimize, and it takes a flash. Done. The matching network is done. In this case, it's only 2 components, and it gives you 2 possibilities. One topology here, another topology, a combination of 2 inductors, for instance. Let's pick up this solution. So we have the antenna booster, and we have the antenna booster with a matching network, and this will represent the transceiver. This port here is the transceiver. It's a combination of a series and a shunt inductance. And let's have a look at the S11 response with the addition of a matching network. In blue, remember, is without matching network, and in pink, we are going to see, wow, it's great response. An S11 below minus 8, and even close to minus 10 dBs in the LoRa frequency bands. And we can repeat this experiment for including all other LoRa frequencies. Let's do perhaps another thing easier. Let's take this component and let's tune it. Let's change the value of this inductance, increasing and decreasing the value. And what you can see is by increasing this value, you can change the response, and perhaps now you can operate in the LoRa in some Chinese frequencies. And also, by tuning, by decreasing the inductance of this value, you can now also operate in for instance, in LoRa in European bands. Even more attractive. Imagine you have this matching network with your fully populated PCB, and once you put the plastic cover, you detect some detuning. Well, it's simple. Then you can retune the antenna when you are close to mass production, if needed, by just tuning the matching network and just shift the response to be within your frequency response. This is something that we have done many times because we don't need to change the antenna. It's very easy to fine-tune the antenna if by any reasons the customer decide to change the plastic cover by aesthetic reasons almost at the end of the project, and well, we can live with that because we can change the matching network. Easy. Okay, next let's move to the second electronic design automation tool we have. For those of you that are designing your devices using a 3D simulator, such as the CST Studio Suite, you can include your PCB, your batteries, your casings. Now, we have in our web page, you can download all our virtual antenna products are encrypted and compatible with CST. So from the RAM extend to the Trio, and we have also user manuals how it's easy to use in your mockup. Here I will illustrate an example. Imagine you have your device fully populated with your transceiver, your ground plane, even your batteries, and so on. So it's easy to go to our web page, download our encrypt models. Let's move this video forward. And by simple steps, just you can put the antenna wherever you want and simulate and do your own stuff. So please go visit our web page and download all the virtual antenna products in case you need for your designs. And it looks like the real product, the same color, same part number, everything looks the same as the real product. Now, let's have a look at the third EDA tool that you can use, either in the simulation phase or in the prototyping phase, in case you want to design your own matching network. So we have plenty of webinar information and tools, and documents, following very simple steps and systematic, in case you want to design with your simulator, you want to include the path effects and some other stuff. We have Opteni that explains in our webinars step by step how you can design your matching network, or perhaps you are in the lab and you want to optimize by your own the matching network by using your own vector network analyzer. So we have materials that explain 1, 2, 3 basic steps that you should do in the lab to do the simulations. And once you get the matching network, just take the matching network, put on your own PCB, and perhaps with a little fine tune, but very simple, you have the antenna operating in the frequency band you want. At this point, you might say, well, but I don't having a background analyzer. I'm not an expert on that. I want just to use this. So there is other EDA tool I can use. Yes, sure. And this is all, by the way, sorry. Here is just to illustrate how this kind of EDA tools based on artificial intelligence are useful. And in here we are comparing a nice design for the Trio MX10 operating on many bands of LTEs, low frequencies and high frequencies. And what we did is we did the matching network using our brain power, and we end up with 7 components. You can see very nice efficiency in pink color in the low frequencies and high frequencies. And we did the same using this kind of systematic approach. And in this case, it was not done by brain power. I mean, you can get your kit and say, well, do this, and do that. It's following steps. And the computer, which has some intelligence inside, the software tell, okay, you need only 6 components. And by the way, not only you need 6 components, 1 component less, but also when we go to the lab and build the matching network, we obtain a behavior that is pretty much, and I would say even better, than the result obtained by the human brain. So at the end, we have to rely on machines. We have the intelligence and we tell the machines how they need to work for us. And we have more free time to do other stuff. So as mentioning, well, perhaps you don't have all these tools. Is there a way that we can support you? Yes, we have this roadmap that we can go with you to accelerate your time to market from proof of concept to design and to qualification. We have all these services. Please have a look at our page, and if any doubt, you can always reach us. But at this point, I will recommend what we have. It's the wireless fast track service, which is at the very beginning and the proof of concept. In this case, what we have is, imagine you have a concept. You don't have a PCB. You don't have any mock-up. You have an idea on how your device should look like. A PCB of 5 centimeters by 10 centimeters, so on, and you want to check if the behavior is going to be good at the very beginning of the project. So precisely, this wireless fast track service requests from you only what is the PCB size and what is the frequency bands you are going to operate. If it's LoRa or you want to combine with other radios. And in return, we tell you which is the best antenna booster. We tell you the bill of materials for the matching network, an estimation of the performance in terms of S11 and efficiency, and also recommendations on how you should shape your PCB in order to get the best of it. Remember, we should work on the antenna system, antenna booster, matching network, and PCB area all together from the very beginning of the project. So if you use this, it's free of charge, and less than 24 hours, we give you in return the report and ready to take action. If it's something is critical, you can take action here, and you are safe because you cannot take risky decisions while you are in design, or perhaps when you are in qualification. This will put your project at stake. Okay, so please pay a visit at the wireless fast track service. It's really very helpful. Now, well, the start of this conference, it's a generic note, which it's a very nice sensor platform, has been designed by our colleagues of the Think Industries, together with the technology of our colleagues of ST Microelectronics, the very nice transceiver, also a microchip. So we are very glad to have our technology here with the 1MX10, glad to be in this kind of ecosystem, cooperating all together in the same direction. Well, you know now, one antenna booster, pretty small, 7mm only, lambda over 50. Also the location, this is something that we have been working very close with the Think Industry colleagues to put the booster as close as the PCB as possible. Also some clearance area to minimize interference. Also the recommendation on how to put the feeding line to reach the transceiver. And by the way, in this case, our colleagues of the Think Industries told us, well, I have an idea of the generic node, but I want to be sure if the size of my generic node is going to be okay, or I may change something. I will need to change to increase the bandwidth, the PCB to get more bandwidth. So they use the wireless fast track service, and in return say, wait, everything looks great, so let's move on. More details. The matching network you can see in here, it's very tiny components. Usually what we recommend is 0402 SMD components. In some other situations, 0201 can work as well, and in some other 0603. What is important is that we should pick high Q and tight tolerance that are available in any vendor. Also, once we have the matching, we have the 50 ohm coplanar wave line, as you can see here, before entering the transceiver phase. In this case, we have a very powerful transceiver system on chip by ST Microelectronics, the STM32WL, which has been presented by our colleague Benjamin yesterday. And it has a very nice option that is a two output power option. One is for 40 dBm for LoRa Europe application and similar, and the other is for 22. So you have two outputs, and it's up to you if you want to combine or you want to have the two outputs together. In this case, there is one switch that combines the two outputs in a single input output. So at the end, we have everything for LoRa Europe and LoRa US in a single port combining together with the 1MX10. This generic node is very attractive because it's twofold. It's a device that you can use it. So forget about hardware. Everything is done. It's plenty of sensors, humidity, accelerometer, many sensors, and even you can add more sensors. So you need only to worry about software. But also, if you want to change by any reason the form factor, or you want to include your own stuff, sensor, and so on, this is a reference design. So you can go, the schematics are open. Our colleagues of the Think Industries, they have everything open. You can check these schematics, change the layout, put your matching network, you do your changes. So this is very, very nice from a device and to a reference design. Also, what we did, it's with our colleagues at the Think Industries, is with this kind of EDA tools, is to check radiation patterns, because what we don't want from our sensor is, okay, do we need to put the sensor in a particular way to receive? No. So let's check the radiation pattern to see if there is in a particular direction. And at the end, what we see with virtual antenna, with this small platform, is that the radiation pattern, it's almost like isotropic. It means that we can send data into the cloud and we can receive from the gateway from any particular direction. So we don't need to worry about how we need to put the device on a particular place. And it's good to estimate this either with simulation or also we can do it with measuring the radiation patterns. Now we are coming to an end. Let's compare virtual antenna with other technologies. And the first one is with the sticker antennas. You know, sticker, it's peel and stick. And well, if you look and have a look at the data sheets, the performance is good. But it's good because, well, the sticker is not mounted on the PCB. And we ask, okay, what happens if we mount the stick on the PCB? Because at the end of the day, what you want is to have a device with everything inside, the transceiver as well as the antenna. So what we have here is a platform with the RAM10 for multi-band IoT frequencies. It's a very small, tiny component, only 12 millimeter length, 3 millimeter width, and only 2.4 millimeter height. And we have compared with a sticker antenna. It's as big as the PCB, it's pretty big. And we have compared for several sizes, the same size as the antenna booster, which is 2.4. We increased to 5, to 10, to 15, and even to 20, which is kind of this very thin, very thick device. And not only that, we have also changed the location, as you will do when putting the antenna on the PCB. And the conclusion is that you can see in this plot, we have efficiencies in the low bands of maybe LoRa or maybe other cellular frequencies. The performance of the virtual antenna outperforms the performance of the sticker. In this case, comparing the sticker on the same height as the virtual antenna, it's amazing, the difference. And even if you increase height, the virtual antenna outperforms. This is one of the main conclusions. In the high bands, more or less the same. Here it's less critical. But again, you can see in red that the performance of virtual antenna is beyond the performance of the sticker antenna. This is critical. And this is the real advantage of this disruptive virtual antenna. Another issue of the sticker antenna that we detected is that when mounting this sticker antenna on several positions, the performance changes. In this graph, we are illustrating the best cases. But if you have the same height and you put in another position, you even can guess even worse values. So this is very, very sensitive on how you mount the sticker on the device. So if you go to mass production and you start mounting this sticker, but with the virtual antenna, it's an off-the-shelf component. So one is fixed, one is optimized on the PCB, you are safe, and you go to mass production with 100% of confidence. So you can scale up your business, you are confident in mass production. Let's have a look at another technology. We are also experts in customized because we have been working, we have in our veins how to design customized antennas. In fact, I can explain my own experience because, well, long time ago, 20 years ago, we have been working in South Korea, developing customized multi-band antennas for the big players, you may guess who, in the South Korea mobile industry. And we were doing pretty nice complex antennas, and we were mastering antennas. We did many designs, and by the way, we won many projects. But at the end of the day, you know what? For every single device we need to design a different antenna. And we thought, wow, this from technical point of view, we can do it. We have the skills, we have the team, and we succeed. But from a business point of perspective, well, you cannot scale because at every project, you are starting from zero. So there is a way that we can do something that we can start not from zero at every single project. And that's the reason why we invented at Fractus Antennas virtual antenna to avoid the pitfalls and the inconvenience of our own customized antennas. So we don't want our customers to suffer the pain of customized antennas, and that's the reason why we invented virtual antenna to overcame the advantage, the pitfalls of customized. Let's have a look at this illustration. By the way, it's published in a very nice magazine, IEEE, Microwave Magazine. You can have a look, where we compare some customized antennas with antenna booster. In a particular for these frequency bands, for multi-band, you can see the volume we get for several samples. It's about 1,000 millimeter cube. But for the antenna booster, it's 10 times smaller, as we saw. In the lab design time, well, we suffer in our veins. You need to do an antenna. If the customer is making some changes on the plastic covers, you need again to tune the antenna, doing some mock-up, going back, tuning, doing another mock-up, do the antenna, and so on. So this is a process that takes weeks and sometimes months to end up with the final antenna, and then you need to qualify the antenna. With antenna boosters, you don't need that, because if the customer needs to make some changes on the PCB, we have the same antenna booster. It's an off-the-shelf. The only thing we need to do in a fast way is to fine-tune the matching network. It is very flexible. Also, well, reuse at other frequencies, as we told before. We receive many projects changing the frequency. We couldn't reuse our own customized antennas. We needed to do from scratch a new antenna. For antenna booster, we can do it. We can reuse the same antenna booster and design a matching network in a systematic and automated fashion. It's easy to integrate. Well, it depends. Antennas were small, but now in IoT devices, we see in some situations very, very slim and narrow devices. And well, if the width is less than 30 millimeter, with customized antennas, maybe very difficult to have, or to say impossible. With the tiny antenna booster, well, there's plenty of place to put the antenna booster. So this is a nice technology, a very powerful technology that avoid the pitfalls and drawbacks of sticker antennas on a sticker antenna technology on one hand, and on the other hand of the customized antennas that we have been working a lot, and we don't want you to suffer again. So just to conclude, some takeaway, some tips. First step, as the chess game, first step matters at all. So you should consider the virtual antenna not only as a component, but as a system. So decide which is the virtual antenna, the position of the booster on your PCB, and most important, also the device size. We should collaborate all together and have also as a trade-off not only marketing decisions, but also performance in terms of radiological performance. You should choose the device size. Virtual antenna can operate at any band, any protocol, any radio, as you saw with the TRIO-MX10, LoRa, Sigfox, also GPS, also Wi-Fi in a single component, thanks to the addition and the simple design of a matching network. Virtual antenna, to give you a very nice takeaway, 10 times smaller than other antenna technologies. It's an off-the-shelf component, ready to use on your PCB. It's a pick and place, so automatically can be placed on your PCB, on your device. We have plenty of tools for you based on electronic design tools. And if not, we have also plenty of supporting tools from the proof of concept down to certification. And finally, the generic node sensor platform, very nice platform for sensoring. It's already incorporating many attractive technology from microchip, ST microelectronics. By the way, the Things network has been designed this device, and including the virtual antenna, the 1MX10 component, which is only 7 by 3 by 1 millimeter. So, well, I hope you find this presentation interesting. I'm happy to be with you today, and please drop by our booth and start and follow the discussion. Stay safe.